Yeah, so my background is actually electrical engineering and physics, but I switched early on to biophysics and came to America in 2003 to do a postdoc at UCSF, where I started to work on microtubular-associated motor proteins. But it was really cytoplasmic dynein, and there are also mutations that cause neurodevelopmental diseases. But when I moved to Einstein, while I continued to work on cytoplasmic dynein, I became interested in KIF1A as well, because it's really highly interesting motor in terms of its biophysical properties. And we talk about the high processivity that KIF1A has, which we call, say, super processive.
What techniques are you using, and what are you hoping to learn about KIF1A through them?
In my lab, we use mainly single molecule technology, even technology that we built on our own, total internal reflection microscopy to visualize fluorescent KIF1A molecules that move along microtubules. And we use optical tweezers, which allows us to measure forces that KIF1A motors generate. The general question we have are really of basic nature. We want to determine, using structure function studies, why KIF1A is super processive, why it can move over more than 20 micrometer along microtubules. Also, KIF1A has a high velocity. It's 2.5 times faster than kinesin 1, the founding member of the kinesin family. And we want to determine why it's so fast. And also KIF1A has really intriguing force generation capability, which we also want to dissect. It easily gives up under load, but it has a high on rate so that it rapidly re-engages so that cargo transport can continue. We became interested in determining disease mutations due to our collaboration with Wendy Zhang in Columbia University and Richard Valley. We have R01 from the NIH together to look at disease mutations, both in vitro and in vivo, and in the clinical setting. And so we have started to screen disease mutants to determine what the effects of particular mutations are.
Talking about the elements that make KIF1 unique, its hyperprocessivity, its quick on rate. Why are these things so important to understand in the context of KIF1A mutations and trying to find therapeutics that either tackle KIF1A mutations directly or impact kinesins more generally?
In general, I think the high on rates are really important in order to ensure cargo transport happens over long distances, because if the on rate would be really low, this would lead to delay in transport. And we talk about, in particular, degenerative effects on the children. And degenerative effects are effects that accumulate. So even if you have a reduced velocity, a reduced on rate, while cargo transport overall still functions, it's slower and takes more time, that this has a long accumulative effects on the children. And so what our aim is to screen for drugs that help these mutants to recover their velocity on rate and force generation. And we use two different approaches for this. One approach is highly advanced. We work together with Atomwise in California, which is a company that does virtual screens. And they have successfully identified 80 molecules, 80 compounds, and they are even being shipped already. They are already on the way to our lab. And we will test these small molecules on the P305L mutant, which is the first mutant that we have characterized in detail. And we hope that some of these molecules can activate or recover function of the P305L mutant. And the idea is, and I can show you, I have here even a list with 83 different molecules that we will receive. And what we will do is, once we have a molecule that looks good or promising, we can order the molecule. We can talk to a chemical company to optimize the molecule based on structures we also solved. And this brings me to the ICSID award that we received a couple of months ago. The ICSID Awards supports our efforts to create a startup company that designs drugs for microtubule-associated motor molecules. But the initial project is only focused on KIF1A. And so our collaborator, Arne Sosa at the Einstein here, who is the leading expert on the cryome structures on microtubule-associated proteins, he has solved successfully the wild-type KIF1A molecule at a little bit better than 3 angstrom, which is a near atomic resolution structure. And he has succeeded to solve the structure of the P305L mutant. The resolution is more 4 angstrom, but it's still good. And our hope is to use the structures, put them in the computer, and perform virtual screens.
That's really an incredible thing because, you know, speaking of KIF1A-Associated Neurological Disorder as an umbrella that spans hundreds of mutations, I think one question that often comes up is, you know, these 2 mutations are so close to one another in the gene, or they're so far apart. Why do the symptoms correlate or not correlate? Why do we have such different diseases across? And so, the hope is to be able to determine that structure, not just in wild type KIF1A, which is a huge hurdle in a lot of approaches that we have, is like, do we know the structure? Do we know the structure? But to actually understand how the shape of KIF1A changes with a given mutation.
Yeah, these are really good points. I can tell you that based on the structure, our structure shows things that no one has seen before, like the K-loop, for instance. We even have the hypothesis that the K-loop might assume different conformations depending on the nucleotide state. But correlating structure, looking at the sites of mutations and the amino acid changes and correlating them with the output, the functional output and the defects we see is really important. It not only allows us to identify drugs that bind specifically to the mutant, but it also allows us to get more information, gain more information in the molecular function of KIF1A. But for us, it's really important that we do a structure-guided drug development. And this is a different approach. Many scientists do high throughput screens with billions of molecules. They have a cell culture and, you know, have a slide chamber or multi-channel system where they flow in drugs and see whether they can rescue KIF1A organelle transport, for instance. But our approach is we take the structure of the mutant and dock the small molecules that we identify in our in vitro assays that have a positive effect. We dock them or we let them bind to the motor. And then we solve the core structure of the mutant with a small molecule bound. And the idea is that we can identify the conformational changes that are induced due to the drug binding. And in addition, we can talk to a chemist, show the core structure and say, what can we do to increase the affinity? Because typically for the small molecule compounds that we receive, we have micromolar affinities, which are not tight. And the lower the affinity is, the less tight it binds, the more likely is it that there are side effects. So we really try to increase the binding strength dramatically by solving the core structure with the promising molecule, talk to a chemist who will redesign and modify the molecule based on the chemical knowledge to increase the binding strength. And that's our hope that down the road, we will have a high affinity binder that has positive effects, recovers velocity, possessivity, and maybe even fourth generation. And this will allow us to have a drug in our hands that will prevent hopefully further degeneration in those children, for instance, that have the P305L mutant. But importantly, we want to develop a high throughput pipeline. So we want to go from mutant to mutant to mutant to mutant, because obviously there are children who have other mutations who have devastating effects. And initially, these are mutants that are in the motor domain because we solved the structure of kinesin, of the food of kinesin sitting on microtubules. And so initially, we will really screen the mutants that are in the motor domain. But in my lab, we also have the effort to express full-length KIF1A in insect cells. And in collaboration with Arne Sosa, we will also try to solve the structure of full-length KIF1A, in particular in the autoinhibitory state, when it's in the monomeric state, when the tail docks onto the motor domain. Also this in the wild-type background as well as the mutant background. But these are efforts that will take more time. But the cryo-EM work on the motor domain of KIF1A bound to microtubules is not only promising, it works. And it's so promising that Anando and I have tried already to submit an R1 grant that covers the basic mechanism of KIF1A, which is my part, and for Anando even screening or determining the cryo-EM high resolution structures of several mutants. Because we try to get NIH funding to cover this line of research.
Going from this, very basic science lens of structure and, changes in response to therapeutics, and then thinking more about, the end goal, which is to hopefully find treatments for the CAN community. Do you have any, last messages or thoughts that you'd like to share with our patient community?
Yeah, I can only say that I'm aware how devastating these KIF1A mutations are for the children as well as for the parents who raise these children in this setting. And I must say I'm really gracious that I can, or my lab can be part of it. And we really hope that we can identify components earlier, even in the next 12 months, hopefully. And I just say, hang in there and support each other. And I hope also that the medical support, in particular related to Wen Nishang, will really help all families who are affected by KIF1A mutations.